Hello. In this unit we will study the rational numbers, denoted as the Q set. Our objectives in this unit include defining the set of rational numbers, the operations of rational numbers, and exploring the properties of these operations. Today we will focus on the operations of rational numbers due to the intrinsic difficulty found by the students in the early years of their degree. The basic requirement for this unit, to make the most of it, is the knowledge of natural numbers and integers along with their possible operations. The origin of Q. Like almost any new number, the origin of new numbers comes from practical problems. In this case, the problem we present here is quite natural. We have 5 pastels to distribute among 3 people, and we are wondering if this is possible. If we distribute them equally, we will have 2 remaining. If we give 2 to each person, we will be short of 1. It appears there is a challenge. In terms of equations, this is equivalent to solving the equation 5 equals 3 times x. Is there a number that is the solution of this equation? The answer is that if we only have natural numbers and integers, that if we remember they are the natural numbers and the natural numbers affected by a sign, then the answer is that no, it is not enough to give us a solution. Therefore, there is a necessity to define new numbers. In this case, the new number is defined as 5 divided by 3, written as 5 over 3. This number is referred to as a fraction, and it represents the following. We divide the unit into 3 parts, represented by the number below, and what we do is take 5 of those new parts, represented by the number above. This way, we aim to divide each part into 3 subparts, and each person takes 5 of those 3 subparts. This results in an equitable and perfect distribution. In general, given 2 integers a and b, as long as b is not 0, we associate this number a divided by b. This number is called a fraction or fractional number. The collection of all these fractions is referred to as the set of rational numbers. But careful, this definition has a fundamental problem, and it's the following. Given the fraction a divided by b. First, let's fix a little notation. The number at the top is called the numerator, while the number at the bottom, which represents the whole of b, is called the denominator. We say that this fraction is canonical if a and b are coprime. This third definition addresses precisely the issue that arises in the definition of Q, which is when the numerator and denominator share common factors. To be coprime means that there is no common factor between a and b. Therefore, when a and b have no common factors, they are considered coprime, and the fraction is termed canonical. An example of this is the following. 3 divided by 5 is a canonical fraction, as 3 and 5 are coprime, having no common factors. However, 3/6 encounter issues as they are not canonical. Since 6 can be factored as 2 times 3, the denominator can be factored as 2 times 3, and we observe that the numerator and the denominator share a common factor, which is 3. We could delete this factor and we would have 1/2. We can observe that, in effect, dividing something into 6 parts and taking 3 of them is equivalent to dividing it into 2 parts and taking just 1. Therefore, 3/6 and 1/2 seem to represent the same idea that we were defining when discussing the rational numbers, and therefore this concept of equality or equivalence is considered. We say that 2 fractions, a divided by b and c divided by d, are equal if a times d is equal to b times c. It's clear from the equation below that we are asserting the equality of the cross products. A times d is equal to b times c. Naturally, extending from the integers, 2 fundamental operations are defined in Q, addition and multiplication. In this case, let's see addition first. Given 2 fractions, a divided by b and c divided by d, addition is defined according to the expression we have here. This expression can always be used, but it is particularly advantageous, or we could say necessary, when the numbers b and d, the 2 denominators, are coprime, meaning they have no common factors. Memorizing the formulas is not useful or practical, but the computational algorithm is very simple. Let's see it with an example. If we have 1/2 plus 4/3, what we do is simply place the product of the denominators in the new denominator. Then, in the numerator, we perform the cross multiplication. 1 times 3 plus 4 times 2. When b and d are very large numbers, the resulting product becomes excessively large, and the numbers involved can become quite annoying. This is why it's advantageous to consider simplification. This simplification can be done when we observe that they are not coprime, and therefore we can find a common multiple for these denominators, denoted as m in the formula, which is the smallest multiple of these denominators. Just like in the case above, memorizing the formula as it is doesn't make sense. The important thing is to understand the process. In this case, as we see in the example of 3/4 plus 5/6, how would we operate? We consider two fractions. Once again, we consider both of them and look at their denominators, which are 4 and 6. We obtain the least common multiple, which in this case is 12, and use it as the new denominator. We want to make the first fraction equivalent to the first fraction equivalent, and the second fraction to be equivalent to the second fraction. To do this, we need to multiply each of these fractions by a number. What number is that? It's the relationship between the new denominators. The relationship between 12 and 4, which is 12 divided by 4, equal to 3, is added to the first fraction. The relationship between 12 and 6, which are the denominators of the second fraction, would give us 12 divided by 6, and is added to the second fraction. Simply, these little numbers that we are adding, which are 12 divided by 4 and 12 divided by 6, always result in integers, because 12 is the least common multiple of the previous denominators. We do this calculation without any additional issues, and in this case we have 19/12. Note that 19/12 is in its canonical form. 19 is a prime number, while 12 is not, but 12 does not have any factors in common with 19. Therefore, there are no common factors, and it represents the canonical form of the result. The other important operation in rationals is multiplication. How is the product of two fractions defined? In this case, it is much more natural. The product of two fractions would be a new fraction, where the numerator is the product of the numerators, and the denominator is the product of the denominators, meaning you multiply what's above and multiply what's below. In this case, 3/5 and 7/6 would be 3 times 7 divided by 5 times 6, resulting in 21/30. Doing the calculation so quickly does have its disadvantages, and it is that normally the fraction obtained is often not in the canonical form of the fraction. That's why the advice we give is that before simplifying, we should try to factorize the fraction and then simplify it. In this case, we can see that the numerator consists of prime factors, 3 and 7. However, the denominator is decomposed. It's formed by the prime number 5 and the non-prime number 6, which can be decomposed as 2 times 3. Once we have this decomposition, we notice that there is now a common factor in the numerator and denominator, which is 3. Therefore, this common factor can be deleted. We have 7 in the numerator and 5 and 2 in the denominator, with no common factors between them. Therefore, we can simplify, resulting in the canonical form of the fraction. The properties of Q in the operations are inherited primarily from those that existed in the integers. These properties are the associative, commutative, the existence of a neutral element for both addition and multiplication, distributive of addition and multiplication, and the existence of the opposite element. What was missing in the integers was the property of the symmetric element for multiplication. In this case, the origin of the rationals is precisely to find a symmetric element for the multiplication operation, which is referred to as the inverse element. Now, given a rational number, we can always find its inverse. Given a, its inverse will be 1 divided by a. In fact, given a fraction, its inverse will consist of simply swapping the numerator and the denominator. The numerator becomes the denominator, and the denominator becomes the numerator. The inverse property states that a number times its inverse, or the inverse times the corresponding number, always results in the neutral element, which is 1. When a numerical set possesses two operations with that style, in fact, any set with two operations with these exact properties is referred to as a field. Hence, we usually speak of the field of rational numbers. Once we have the existence of the additive inverse and the multiplicative inverse, we can define the inverse operations for addition and multiplication. In a fairly natural way, subtraction is defined through addition as the additive inverse. So the fraction a divided by b minus c divided by d is actually equivalent to adding the first fraction to the additive inverse of the second. In an example, we have 3 divided by 5 minus 4 divided by 7, and the operation essentially consists of adding 3 divided by 5 to the additive inverse of 4 divided by 7. In practice, we consider the minus 4 as the numerator and the 7 as the denominator. Here is the operation, which simplifies to 1 divided by 35. The division is exactly the same. To define division, we multiply by the multiplicative inverse. So if I want to divide a divided by b divided by c divided by d, what I do is multiply by d divided by c. We reverse the order. Here's another example. 3/5 divided by 4/7 would essentially be 3/5 times 7/4. We reverse the number and we get the result. Well, that's it for now. In this unit, we've covered the definition of rational numbers, the fundamental operations of the set of rational numbers, and the properties of these operations in Q. Thank you.